Welcome back everyone. In the last lecture, we had seen how to design state feedback controllers so that we can change the eigenvalues of the system. And at the end of the lecture, I had asked 3 questions. The questions were, in this setup where we have taken a controller of the form u equal to minus kx, the first question we asked was, are the states always available? Because if the states are not available, we won't be able to implement this control law. The second question was, what happens if the system is uncontrollable? Because all these things that we have done in the last lectures was with the assumption that the system is controllable. Now, the third question was, how will the system know where to go? In this setup, if we place the eigenvalues of a minus bk such that they are all in the left half plane, we know that at t tending to infinity, the solution of this equation, which is of the form e to the power of a minus bk whole t x of 0, this solution will always go to 0 as t tends to infinity. But all systems won't have that as your specification. For example, instead of going to 0, I want to reach to say some particular value, suppose 1 or 2, maybe that quadrotor example that we took. In that example, we wanted to go from ground to a particular point. So, this control law will not help us to get to that point because all the states are dying to 0. What to do then? So, these were the 3 questions that I had posed in the last lecture, and today we will try to answer the second question, what happens if the system is uncontrollable? Consider that we have a system x dot equal to ax plus bu and we define this new state variable z, and you remember if we take t to be in some nice form, then we can get either to the Jordan canonical form or the controller canonical form that we had seen in the last few lectures. Today we will be constructing a new T matrix which will help us to decompose an uncontrollable system. Let us see how we are going to do that. The assumption here is that the system is a seesaw system and it is uncontrollable. Now, since the system is uncontrollable, we know that the rank of the controllability matrix will be less than n. Let us say that the rank of that matrix is R, which means that if I find image of CAB, there will be exactly R number of basis vectors for image of CAB. Image of CAB is a subspace, right, because CAB is a matrix, image of CAB is nothing but the column space, and since it is a subspace, it will have basis vectors, and say it will have R basis vectors because the rank of the matrix here is R. It must have R number of basis vectors. Now, what will be the basis vectors? So, we can choose the basis vectors as b, ab up to a to the power of r minus 1b. So, because if you take a to the power of rb, it is guaranteed that a to the power of rb will depend upon the vectors b, a, b, a to the power of r minus 1b, because we know that image of CAB, since image of CAB has dimension r, so there must be r basis vectors, and which are the basis vectors that we can choose? We are choosing the basis vectors to be b, a, b up to a to the power of r minus 1b. Now, if these are the basis vectors, I will define a Q matrix of the form b, a, b, a to the power of r minus 1b. So, I have r columns here, and then I will add another n minus r columns. And what are these columns? We will add these columns in such a way that this matrix, which is an n cross n matrix, will become invertible. So, I can always choose columns here, add columns here such that this matrix becomes invertible. Now, we will choose the transformation matrix T here to be Q inverse. We will choose T to be Q inverse. Again, why are we doing this? We are doing this so that we can decompose the uncontrollable system into two different systems. You will see what those systems are, and those systems will give us more information about the system that we are working with. So, this is the recipe of creating that canonical form, and this canonical form will be called controllability canonical form. And how do we get to that form? First of all, the system of course has to be uncontrollable. If the system is uncontrollable, we know that the rank of the controllability matrix will be less than n. Let us say that the rank of the controllability matrix is R. If the rank of the controllability matrix is R, we know that image of CAB, which is a subspace, must have R number of basis vectors, and we can choose those basis vectors as B, A, B up to a to the power of r minus 1 b. These will turn out to be linearly independent. This can be proven actually. If what can be proven? If the rank of CAB is equal to R, then BAB up to a r minus 1 b will be linearly independent. This can be proven. And remember, these are n cross 1 column vectors. These are column vectors here. So, I have collected r number of column vectors. I take those r number of column vectors, and then to that I append n minus r more columns such that Q becomes invertible. Remember, Q is a square matrix here, and then I choose T equal to Q inverse. As soon as I choose T equal to Q inverse, so this becomes Q inverse. I can take Q inverse to the left. So, the transformation can be also written in this way, that we are going for a transformation of the form Qz equal to x. If we go for such a transformation, then A hat here will turn out to be Q inverse of AQ, B hat here will turn out to be Q inverse of V, C hat will become CQ, and D hat remains as D. This we have done quite a lot in this lectures, because we have been forming this new canonical form every time. So, till now we came up with two canonical form. One was the Jordan or the diagonal canonical form, other was the phase variable form. So, now we are going for another form. Remember, this is an uncontrollable system. For an uncontrollable system, we are going for another form. Now, let us find out, if we choose T equal to Q inverse, then what type of form do we get? So, if we choose T equal to Q inverse, notice that A hat was Q inverse of AQ. So, I can write AQ equal to Q A hat, and that means now if I take take the left hand side here, the left hand side is A into Q. This was your Q. If I multiply out, so what do we get? AB, A square B, A to the power of RB, and then here it will be AG1, AGN minus R. Notice that this term here must be dependent on B, AB up to AR minus 1B, because if it was not dependent, if A to the power of RB does not depend on B, AB to A to the power of R minus 1B, the rank of this matrix would have become R plus 1. This matrix would have, so if I take this as the controllability matrix, you see, if A to the power of RB does not depend on these terms, then A to the power of RB cannot be written down as linear combination of these terms, which means that the rank of this matrix then will turn out to be R plus 1. But to start off with, we have already assumed that the rank of this matrix is R. So, therefore, this A to the power R can be written as linear combination of B to A to the power of R minus 1B. Now, once we know that we can do that, you see, I am writing A to the power of RB as linear combination of this. Now, I do not know what the linear combination would be, it depends on the value of A and B, but in general I can always write this. Now, what is the advantage here? You will see the advantage soon. You see, what are we trying to do again? A of Q is equal to Q of A hat. The left hand side is giving us this. Now, on the right hand side, I can write Q here. This is my Q, and A hat is, this will be my A hat. I want to write down what A hat would be. Okay. So, this is your AQ, and after AQ multiplication, this is what we get, and on the right hand side we have Q into A hat. So, I have to fill up this part, this matrix, so that this equation is valid. So, let us try to see what happens. Now, on the left hand side of this equation, let us look at the first column. What do we get? The first column here is A, B, and in this part, if I have to get A, B, I have to somehow pick the second column here, which means I have to write 0, 1 dot 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 0, 0 dot 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 0. So, 0 times first column plus 1 times second column plus 0 times of the other columns will give me the second column, which is exactly equal to the first column on the left hand side, and that is what we are writing here. And by now you know then what will be the second column here. The second column is A square B. So, which means the second column of A hat should become this. If you keep on doing this, you will see that at this point we have the linear combinations of B to A to the power of r minus 1 B. So, what is this? This is nothing but gamma naught times of B, gamma 1 times of A B plus gamma 2 times of A square B plus dot 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 gamma r minus 1 A to the power of r minus 1 B. So, here you see that this is gamma naught times of B plus gamma 1 times of A B dot 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 gamma r plus 1 times of this, and then the bottom part here is multiplied with 0. So, this gives us the first part. Now, what about this one? Okay, what is A of G1? See, G1 I had chosen arbitrarily, right? G1 I could choose anything. So, A of G1 will be a new vector, will be an n cross 1 vector, which can be linear combination of any of the vectors here, right? Because A of G1 will be a new vector, it is an n cross 1 vector, and since this matrix is invertible, all these terms are linearly independent of each other. In other words, all these vectors can be considered to be basis of Rn. So, that means any vector in Rn can be written down as linear combination of all the column vectors here, and since A of G1 is a vector in Rn, so therefore, A of G1 must also be written down as some linear combination of the columns of this matrix Q. And what is that linear combination? I am choosing that, suppose f of f. So, what I am saying is that A of G1 is equal to suppose f11 B plus f21 AB plus dot 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 f of n1 A G n minus r, and that is what is being written down here. In the same way, AG2 and same way AGN minus r also can be written down, and this is what the A hat matrix will look like. Remember, this was your Q, this is your A hat, this is your A, and this is your Q. So, A hat has this nice structure. What is the structure like? You can see that I can draw a line here, and this part is a block matrix, this is another block of matrix, and this is another block of matrix here, and there will be a 0 sitting over here. Okay. And this is basically what we will call a block upper triangular matrix, and we call this upper part here to be AC, here this part we will call AUC, and this we are calling as A bar, and this was a 0 matrix anyway. What are the dimension of these matrices? You can see that this part is an R cross R matrix. What was R? R as the dimension of the controllable space or image of CAB. Dimension of image of CAB was R. So, AC is a R cross R square matrix, whereas A of UC here would be a n minus R cross n minus R square matrix. So, what will be A bar here? A bar is a R cross n minus r matrix, but it is not square. Okay. Now, this will reveal lot of information about the system. Now, before that, let us look at what will be B hat like. A hat we have found out. A hat has a nice structure, AC, A bar, 0, AUC. This is the structure of A hat. Let us look at B hat. What will be B hat like? What is B hat? B hat is equal to Q inverse of B, right. So, we can write Q B hat equal to, so Q B hat is equal to B. So, now I just have to find out what will be B hat, and since on the left hand side we have B, so I just have to pick out this column. So, which means B hat should be 1 0 0 this. So, here I can consider this to be an R cross 1 vector, and this is an n minus R cross 1 vector. Now, the top part here we will call B1 and the bottom part will be 0. Okay. So, finally, what is the structure we are getting? So, A hat came out to be a block upper triangular matrix and B hat comes out to be B1 0. Okay. And what about C hat and D hat? See, C hat and D hat might be anything, because when we constructed the Q matrix we used only B and AB. So, only A hat and B hat will have some nice structure. C hat never came into the picture of constructing the Q matrix. So, therefore, C hat will not have any particular structure as such. Similar is the case for D hat, because in this case D hat will exactly be equal to D. Okay. In the previous canonical forms also, when we were choosing the transition matrices or the transformations, in that case also we only used A and B to come up with the transformations or the T matrix, and therefore, in those cases also C hat and D hat was not having any particular structure as such. So, what does this reveal about the system? Notice again, let me just recap. What did we do? We took a seesaw system which is uncontrollable. Since it is uncontrollable, we know that the dimension of the controllable space will be less than n. Suppose the dimension is r, which is less than n. Now, since it is r, we can choose the first r columns of the controllability matrix CAB, which is B, AB up to a to the power r minus 1b. These have to be linearly independent. We choose them as a basis of the controllable space. Once we check that, we can extend that basis or we can add more columns such that this matrix becomes an n cross n invertible matrix. This is again always doable. Now, once we have done that, if we use Q z equal to x transformation, then A hat here turns out to be a block upper triangular matrix. Q inverse of B or B hat comes out to be a matrix of this form, and CQ will come out to be C1 C2. Why C1 C2? Again, C1 and C2 can have any values. We are just keeping it conforming to the partition here. Now, what do you mean by conforming to the partition here? AC was r cross r and this was n minus r, n minus r. Similarly, here it was r cross 1 and then n minus r cross 1, 0 part, and this one would be, since it is a seesaw system, 1 cross r and then n minus r here. So, this is what the partitioning would look like. Now, what does this reveal about the system? Let us look at the equations now. See, this same equation I can write down the states, the transform states ZT. I can divide them up into two parts, where this is, of course, this Z here, ZT is here is equal to Z1 and Z2, and this is an n cross 1 vector, where this top part is r cross 1 and the bottom part is n minus r cross 1. Okay. So, here when we look at this differential equation, so this is the differential equation after the transformation, this is the output equation after the transformation. Now, if I open these brackets up, what do I get? The equations that I will get is Z1 dot equal to AC Z1 plus A1 Z2 plus B1 UT, and Z2 dot is equal to AU and Z2T. Now, you look at these two equations. So, basically what we have done is we took a system, the original system or the plant state equation, which was this state and output equation, which was this. We took this system, we converted to this to a new form of this. These are the new differential equations and they are related by Qz equal to x. Now, what does it tell us about the two systems? Now, look at this. If I ask you what will be the solution of the second equation here, you can directly tell me that Z2T must come out to be e to the power of AUN T Z20, right, because we know what will be the solution of this type of an equation. So, this will be the solution of this equation, and what is important to note here is that Z2 is not influenced by any input. Okay, the input u that is there is not influencing Z2, which means what if once you fix the initial condition of Z2 0, Z2 t will evolve on its own. You have no control or you cannot change the Z2 based on the inputs that you are choosing, and that is why this part of the differential equation represents the uncontrollable part of the system. Okay, and that is why I have written a UN here. I will explain what does this uncontrollability mean here also, but let us look at the from the solution of the equation point of view. Let us see what it means. So, this is the solution of the second equation. What about the first equation? In the first equation you can see that this part I can consider to be the new input. So, Z1 t will come out to be e to the power of a c t Z1 0 plus integration 0 to t e to the power of a c t minus tau a1 z2 t plus b1 or a1 z tau z2 t tau plus b1 u tau d tau. So, this will be the solution of the second equation, and in the second equation you can note that the Z1 t can be influenced by the input. Okay, although Z2 is coming in here, but it can be influenced by the input, whereas in the first equation the input or the second equation here the input had no role to play, which means the second part of the differential equation, the last n minus r differential equation, we will not be able to influence those state variables. So, remember what is Z1, Z2? Z1 and Z2 is a state vector, which means the elements of these state vectors are state variables, right. Although it might not have any physical meaning because we have transformed the system, but nevertheless these are state variables, and what we are claiming with this transformation is that the last n minus r state variables we will not be able to control because they will just depend on the initial condition of those state variables, whereas the first r state variables in this form can be controlled because I have a u which will influence that. As a matter of fact, you can go ahead and prove that if you take AC and B1, AC B1 is a controllable system, which means that the rank of the controllability matrix corresponding to AC and B1 will come out to be R. Let us take an example that we had already done in previous lecture and try to see what does it mean by whatever we are talking here. So, remember this example, the question was that we have to find out an input ut such the capacitor voltages are 2 volt and 1 volt respectively, and this has to be at 1 second if initially the capacitors are discharged, and this was the solution that we tried to find out, and we found that there will be no solution for this example. Okay, and this was an uncontrollable system because the rank of the controllability matrix here was 1. Now, if I use the ideas that we have just now learned, since the rank of the controllability matrix is 1 here, we know that the first the image of CAB will be given by span of B, right, because we can take the first vector here, B we will take. So, image of CAB is equal to span of 1 1 here. So, the Q matrix I can construct in this way. Again remember this is a 2 cross 2 matrix. So, therefore, Q matrix will also come to be 2 cross 2. The first column here is B, and then so basically this is your R here. So, that means B a to the up to a to the power r minus 1 B we had to go, right, since R is equal to 1 here. So, I will just have one column for the controllable part. So, 1 1, and then I can choose anything. This is your G1, I can choose anything here so that Q matrix becomes invertible. So, I chose 0 1, you can come up with anything else also. Once I have done that, you see what is Z1 Z2, Z1 Z2 is Q inverse of X. Remember X has a physical meaning here, the state vector X are nothing but the capacitor voltages of C1 and C2. So, here Z1 Z2 equal to this, again if I go ahead and multiply, this will be the new state variables that we are getting. Remember we started with x1 and x2, these are physical state variables that we took. This was capacitor voltage 1 and voltage across the capacitor C2. Now, after the transformation the state variable becomes something like this, Vc1 and Vc2 minus Vc1. Now, this does not have, the second variable at least does not have any physical meaning as such. We can tell that okay, this is the difference between the two capacitor voltages. However, suppose tomorrow I come up with 2 here. So, in that case of course, the new state variable Z1 and Z2 will have some different meaning altogether, because if I take 2 here, I have to do an Q inverse of that, and then this matrix will come out to be something different. But what is important here to note is that once I use this Q matrix to get to the controllability canonical form. So, the controllability canonical form will come out to be this is nothing but Q inverse of AQ, where A is this, and this is Q inverse of B, where B is this. Okay. And you can see nicely, since R is 1 here, we know that AC will be a 1 cross 1 matrix, this is an 1 cross 1 matrix, and AUN, since N is 2 and R is 1, so N minus R is 1, so AUN will be a 1 cross 1 matrix, this is that 1 cross 1 matrix. In this case, A bar came out to be 0, it is not always possible that A bar will come out to be 0, it can be something else also. So, we have a block upper triangular, in this example at least a block diagonal matrix, and now what is important to note here is that the equations, what are the differential equations that we will get? You see, the differential equations that we will get is Z1 dot is equal to minus Z1 plus Vt, and then Z2 dot is equal to minus Z2. Okay. Now, what is the meaning of that? So, what was Z2? Z2 t will come out to be e to the power of minus t Z2 0, which means Vc2 minus Vc1, which was nothing but Z2, this will be equal to e to the power of minus t Vc2 minus Vc1 0. From the first equation, using V, I can change Z1. Z1 was voltage across the capacitor C1. So, physically it means that I can change the voltage across the capacitor of C1 as I desire. If you give me any initial condition, I would be able to go from any initial condition for Vc1 here to any other point, okay, any other value within a finite time. However, once I fix that, once I suppose go from Vc1 0 to Vc1 t say Tf say, Vc2 Tf will get fixed, because Vc2 Tf minus Vc1 Tf is governed by this equation. So, Vc2 minus Vc1 Tf will be equal to e to the power of minus Tf Vc2 minus Vc1 0, and this will get fixed. So, so in this case you can see that it only depends upon the initial condition of Vc2 minus Vc1. You cannot give me any arbitrary point, say okay, suppose initially the capacitors are charged and you need to go to say 3 1. This is not possible, because you can only take care of okay, in this example this is Vc1 and Vc2. So, in the transformed matrix or the transform vector, in the transform vector this will be your Z, Vc1 and Vc2 minus Vc1. So, I have to go from here to 3 minus 1 is 2. So, to this point. So, in the transformed system I have to go from 0 0 to 3 2. Okay, but this is not possible, because this is an uncontrollable system, and we have shown that we can change from 0 to 3, but we will not be able to influence to go from 0 to 2, because this will depend upon the initial conditions. Okay, I hope physically you have understood the meaning. See, one important point to note here is that in this example, since I took Q such a way that this came out to be a capacitor voltage 1, it had direct physical meaning. So, in case if you would have taken here a 2, then or anything else here, because this depends on you what you choose, then Z1 Z2 won't come out to be in this nice form. It will be some linear combinations of Vc1 and Vc2. In that case you won't have a direct physical interpretation. However, you will see that going to this nice form of upper diagonal or upper triangular block triangular matrices, upper triangular matrices, we would be able to design the feedback controllers for uncontrollable systems also. Of course, there will be some things which we won't be able to do. I will talk about that soon. Okay. So, let us look at another example where we will see how to decompose the decompose an uncontrollable system. So, suppose this is the system that we have, this is the matrix that we have, and we are asking first whether the system is controllable. We can see that the system will turn out to be an uncontrollable system, and not only that the rank of the matrix is controllability matrix is 1, which means R equal to 1. So, we are expecting AC to be a 1 cross 1 matrix and a UN to be a 2 cross 2 matrix. So, let us choose Q now. Since R is 1, we know that we can only choose one linearly independent vector from C of AB, that is the B we are choosing. So, B we have chosen like this, and then the other two vectors, since we have to make it a 3 cross 3 invertible matrix, I can choose this. You can go ahead and choose something else also. Once I have chosen that, I will choose QZ equal to X. If I apply that transformation, the new state equations in terms of Z will come out to be of this form. Now, what is Q inverse of AQ? Q inverse of AQ will come out to be of this form, and as expected AC here is a 1 cross 1 matrix and AUN here is a 2 cross 2 matrix. Okay. And where is B is again B1 0, where B1 is a R cross 1 matrix and 0 here is an N minus R cross 1 matrix. So, once you get this, these are the so I can rewrite the equations, and this will be the equation. This Z1 I will be able to influence with the help of an input, but Z1, Z2 and Z3 I won't be able to influence with the help of an input. So, this will become the uncontrollable state variables, of course a transform state variables. So, these becomes the uncontrollable state variables, okay, and this will become the controllable state variable. Remember, the state space dimension is still 3. What do you mean by state space dimension? The state vectors are still of dimension 3 cross 1. In this transformed state variable, I can only change the top part, the first element here from anywhere to anywhere in fixed time, in a finite time, and the bottom part, which is a 2 cross 1 matrix, that I won't be able to change as I wish. Okay, that is the uncontrollable state variables. Now, till now I have been talking about seesaw systems, right, and in seesaw system this is how we have been doing the entire we have been solving the entire problem. Now, when we talk about a MIMO system, so as soon as I talk about a MIMO system, this become an N cross M matrix, this remains N cross N, this becomes a P cross N matrix, and this becomes a P cross M matrix, right. So, now also I can go ahead and check what is image of CAB's dimension, or what is the rank of CAB. If the rank of CAB is R, again I know that image of CAB dimension, the dimension of the subspace image of CAB will also come out to be R. And what is the meaning of that? The meaning of that is, for image of CAB I would be able to find out R linearly independent basis vector, R linearly independent vectors that spans the space. In other words, the basis of image of CAB will have R number of basis vectors. Now, the question is, how do I choose those R numbers? In the seesaw case, what we did was, remember in the seesaw case it was x dot equal to Ax plus Bu, B was a column vector, n cross 1 column vector. So, if the dimension of image of CAB came out to be R, we chose the first vector to be B, which is 1 column vector. Then we did A of B, which we got another n cross 1 vector, and this way up to A to the power of R minus 1 B, we can go ahead and get R linearly independent vectors. Once we have R linearly independent vector, we then appended here n minus R more columns, so that this becomes a square matrix, right. Now, in this case, remember in the MIMO case, the problem is that this is an n cross M matrix. Now, I cannot go and say that you choose the first column to be B, because B is an n cross M matrix now, it is not a column. So, how do I choose, how do I go ahead and do the same idea? Now, it is very easy to do that, because what we can do is, we can replace this B to A to the power of R minus 1 B, which we did for the seesaw case, with a basis of image of CAB. Okay, you can come up with any basis of image of CAB. We know that image of CAB, since it is the dimension of this space is R, it will have R number of basis vectors. So, we will stack R number of basis vectors here. Okay, and once I stack that up, after that I can again go ahead with the same idea that I add more vectors here to make Q as a invertible matrix. Okay, let us take an example and look at this problem. So, this is suppose your MIMO system x dot equal to Ax plus Bu, and we will see that if I go ahead and find out the controllability matrix, this will be the controllability matrix B A B A square B. Now, it is a fat matrix because it is a MIMO system, and you can see what will be the rank of this matrix. The rank of this matrix will come out to be 2. Go ahead and check that. You see this and this are dependent. So, of course, now I just have to check whether this is dependent on these two, and you can see that yes, this is dependent on these two, because if I subtract this from this, we will get 1 0 minus 1. So, the rank of CAB here is actually 2. So, which means R is equal to 2, which means when I construct the Q matrix, the first 2 columns of the Q matrix will be from image, will be a basis of image of CAB, and then we will have another column here which will be say some arbitrary vector G1, which will make the Q matrix invertible. Again, remember, the Q matrix here is a 3 cross 3 matrix. Whenever in doubt, you go and write down the dimension of the matrix. So, in this case, Q will be a 3 cross 3 matrix, because we have to do Q inverse of AQ, right, and Q inverse of AQ, you see this is 3 cross 3, this better be 3 cross 3 and this better be 3 cross 3. So, that total you get a new matrix which is 3 cross 3. So, this way also you can remember, you see Q will come out to be a 3 cross 3 matrix. Now, what is the Q matrix that we will choose? Now, a easy way of finding out the basis vector for image of CAB for the MIMO case is this. Let me say that this is your first column vector. I am first column of the B matrix, I am calling it to be B1. The second column of the B matrix I am calling to be B2, and now with B1 you can see when I am writing B A B A square B, the first this column is B1, this column is A B1, and this column is A square B1. You can check. Okay. Similarly, the other two, this is B2, this is A B2, and this is A square B2. Okay. As a whole, these two was B, these two was AB, and this two was A square B. Go ahead and check. This will be, you can go ahead and check, carefully check this. Okay. Now, what we can do is using, since we know that the image of CAB will come out to be 2, dimension to be 2, I note that I need 2 vectors only, and directly from here I can see that these 2 itself will become your basis vectors, because they are linearly independent. So, I can choose the first 2 vectors to be B itself, and the last one I can arbitrarily choose, I am choosing it to be 0 0 1 to make it invertible. Once I use this transformation, this is what I will get. This will be the controllability canonical form, and once I have this form, you can directly see that this will be the controllable part and this will be the uncontrollable part here. So, this is how we can go ahead, and find out the controllability canonical form for an uncontrollable system. Remember that whatever I did for CISO has been extended to MIMO now. Now, whatever method I told for MIMO, this actually works for CISO also, right. So, why are we doing this? Now, notice that what we have done, we have decomposed the system into 2 parts in some way, and what we will see that using this decomposition we can come up with a state feedback controller that we want to change the eigenvalues of the actual system. Now, this block upper triangular form also gives us some more informations about the system, and this brings us to what is known as the PVH test. So, A will have eigenvalues, right, because A is an n cross n matrix, A will have n number of eigenvalues. Now, it turns out that if A has n number of eigenvalues, the eigenvalues of n can be classified into 2 parts, and that is the classification we are looking into now. What is A? A is an n cross n matrix. A minus lambda I is another n cross n matrix, and to that I am appending B. So, this becomes an n cross n and this is an M. So, n cross M, this is an n cross n plus M matrix, okay. And the rank of this matrix, if you keep on, you can keep on plugging different values of lambda here, right, okay. So, if you plug an eigenvalue of A here such that the rank of A minus lambda I B comes out to be n, that eigenvalue will be called a controllable eigenvalue of the system. Again, if you plug in an eigenvalue of A here and the rank of this matrix comes out to be less than n, then that eigenvalue will be called an uncontrollable eigenvalue of A. Okay. See, remember here this lambda I can keep on changing. So, I can take anything from the complex plane. Think about it, I can take anything from the complex plane and ask this question. Okay. Suppose I take this point and this is not an eigenvalue of A. If I put this eigenvalue at this point, so A minus lambda I will come out to be a matrix and B will be another matrix. Now, in that case, will this, what will be the rank of this matrix? You see, since A minus A, since this point is not an eigenvalue of A, so the rank of A minus lambda I will always come out to be n. So, which means this will anyways come out to be n. So, the rank of this matrix will come out to be n if you check in any point on the complex plane which is not an eigenvalue of A. Only important point are the points where when lambda is an eigenvalue of A. So, lambda will have n eigenvalues, lambda 1, lambda 2 to lambda n. What we are saying is that for those lambdas for which the rank of this matrix comes out to be n, we will call them controllable eigenvalues, and the ones for which it is not, we will call them uncontrollable eigenvalues. Okay. So, this is the difference between a controllable eigenvalue and an uncontrollable eigenvalue. Now, again this has a nice link with the block upper triangular form that we got. So, the block upper triangular form that we got was this. Remember, the original system is this and this is the block upper triangular form. What is the link of eigenvalues? What are the eigenvalues? How are the eigenvalues of this A matrix related to the eigenvalues of this matrix? Remember, what is A hat? This was your A hat. So, A hat is nothing but Q inverse of A Q, and which means the eigenvalues of A hat and the eigenvalues of A will be the same, because this kind of transformation do not change the eigenvalues because the characteristic equations are not changing. We have already done this type of things earlier also. So, the eigenvalues of this matrix is nothing but the eigenvalues of the matrix A. Now, the good thing about this is, notice that the eigenvalues here, the eigenvalues of the matrix A can be written down in this way. So, the eigenvalues of the matrix A are nothing but the eigenvalues of AC union the eigenvalues of AUN. Again, here when I am saying eigenvalues of AC, all multiplicities are included. Okay. So, but what I mean to say is that suppose lambda of A is 1 1 3 2, okay, and the eigenvalue of AC comes out to be 1 3 and the eigenvalue of AUN comes out to be 1 2. Okay. So, if you take the union, in general when you take set unions, multiplicities are not considered, right, but in this case we are considering multiplicities. Okay. When I am talking about union here, I am considering multiplicities. So, basically, so this is true, this will be true, and why is that? You see, what are the eigenvalues of this matrix? The eigenvalues of this matrix are determinant of roots of determinant of SI, AC, A1, 0 or A bar, whatever you want to say, that AUN, this is what it is, and this is nothing but, this is an n cross n matrix, this is nothing but determinant of S into, I can call this an R cross R identity matrix, 0 0, n minus R cross n minus R identity matrix, okay, this minus AC A1 0 AUN, right, and what is this? This is nothing but determinant of SIR minus AC multiplied by determinant of SIN minus R minus AUN. So, the determinant of SI minus this matrix is nothing but determinant of SI minus Si minus Ac into determinant of Si n minus Aun, but what is this? These are the roots of these are eigenvalues of Ac, the roots of these are the eigenvalues of Aun. That is why the eigenvalues of an upper triangular or upper block triangular matrix are the eigenvalues of the union of the block triangular matrix. Union of the eigenvalues of the block triangular matrix will give you the eigenvalues of this upper block upper triangular matrix, and we know that the eigenvalues of this matrix are the same as the eigenvalues of the actual A matrix, because they are related by a similarity transform. Now, what does this tell us? You see, the good thing now is, notice that now I know which eigenvalues are what. So, sum of the entire eigenvalue set of A can be divided into some eigenvalues from here and the others from here. Now, suppose I take an eigenvalue from this point. So, and use this test, say rank of A C A1 0 AUN minus lambda UC IR 0 0 I n minus R, this, and here we will have B1 0. This will be the rank test. Now, what is this coming out to be? Rank of AC minus AUCR IR minus A1 B1 A 0 here, 0 here, A U n minus lambda U c I n minus R 0 here. This will be the matrix, right. Now, what is the rank of this matrix? Is lambda U c an eigenvalue of A c? No, lambda U c is not an eigenvalue of A c. So, the rank of this matrix will come out to be R, right, because A c is a R cross R matrix. So, and what about this? You know that lambda of U c is an eigenvalue of A u n, which means that the rank of this matrix must come out to be less than n minus R. So, the rank of this matrix will be less than n minus R, okay, because why? Because this is an eigenvalue, and I know that if it is an eigenvalue, it must satisfy. So, if lambda U c is an eigenvalue, it must satisfy this, right. V is equal to lambda U c I n minus R, this must be satisfied, but what is this? This is nothing but A u n minus lambda U c I n minus R V equal to 0, and we know that the eigenvector is non-zero. So, that means that A u n minus lambda U c I n minus R I n minus R must be a singular matrix, and the rank of this matrix has to be less than n minus R, because I must find some vector in the kernel of this matrix. Okay. So, that is the reason that for the eigenvalues of A u n or the uncontrollable part or the uncontrollable block, the eigenvalues of A u n will lead to a decrease in rank, because this was R and this never came out to be n minus R. The rank of this never came out to be n minus R. This is a 0, this is a 0. So, therefore, the rank of this part will have to be less than n minus R. So, in total the rank will always come out to be less than n, and that is why the eigenvalues of this part will be called uncontrollable eigenvalues of the system. So, when I defined this controllable and uncontrollable eigenvalues, I did not choose a specific form of A, right. You do not have to choose a specific form of A, but the good thing about the transformation that we had done is, when we transform the system into this block upper triangular matrices, I can directly see what are the uncontrollable eigenvalues and what are the controllable eigenvalues. The eigenvalues of this part will become uncontrollable. So, if you check what are the eigenvalues here and check the rank of this matrix, it will always come out to be less than n, and the eigenvalues of this part will come out to be controllable. Okay. Sigma AC, the eigenvalues of AC are the controllable eigenvalues of A, and the eigenvalues of AUC or AUN are the uncontrollable eigenvalues of A. if I go ahead and take the example that I have given just now, this was the example that we had taken, and you see in this example we know that this is an uncontrollable system. So, once I get to the block form, so this was my AC, and what are the eigenvalues of this matrix? The eigenvalues of this matrix, since this is an upper triangular matrix, the eigenvalues of this matrix are 0 and -1. So, these are the controllable eigenvalues, and the eigenvalues of this part is -2. So, this is an uncontrollable eigenvalue. So, we can check, you see I have taken the A and B matrices here. Now, I will go ahead and check rank of A minus lambda I B. See, this is the A and B matrix that I have chosen, and the lambda first I will choose from here, and then I will choose from here. So, if I start with -1, so let us see. So, you see rank of A minus of -1 I, B will give me 3, rank of, yeah, if I go ahead and complete the entire thing, you see. So, you see -1, the rank is 3, this is n is equal to 3 here. So, -1 is a controllable eigenvalue, 0 is a controllable eigenvalue, -2 is an uncontrollable eigenvalue. Okay. So, this is how we can differentiate between what is controllable and what is uncontrollable. This brings us to the PBH test. Okay. Now, what is this PBH test? You remember this controllability statements that we had got, the equivalent statements. A system is said to be AB controllable if the controllability Gramian is non-singular for all time t greater than 0, and also if we take the controllability matrix and its rank come out to be n, then also we say that the system is controllable, and all these three statements are equivalent to each other. Now, the PBH test tells that, you see, think about it. Before I get to the PBH test, think about it. If the system is controllable to start off with, what will happen to rank of A minus lambda I B? You see, if the system is controllable, I know that when I try to find out the controllability canonical form for A, it will only come out to be AC only, right, because there is no uncontrollable part in this case. So, that means all the eigenvalues of A must be controllable, which means that the rank of A minus lambda I B is equal to n for all eigenvalues of A. For controllability, a system is controllable if and only if rank of A minus lambda I B is equal to n for all eigenvalues of A, and this is what the PBH test is. The PBH test to check whether a system is controllable or not. However, this PBH test has more information. It not only just tests whether a system is controllable or not, if a system is not controllable, which are the eigenvalues which are not controllable can also be checked using the PBH test, because the rank of this matrix will then come out to be less than n. So, this is what the PBH test tells us. So, what are the things that we have gone through? We have first taken an uncontrollable system. Okay, we took an uncontrollable system first, and then we checked how to get to the controllability canonical form. If the system is uncontrollable, I can change the matrix, transform the state matrix and the B matrix to this nice form, and this is true for MIMO case also. Only thing that I have to do is Q I have to take in such a way that the first R columns are here from image of our basis of image of the controllable space, and then I can extend this to make it into a square matrix and then use QZ equal to X to get to this form. Once I get to this form, I can directly, if looking at this form itself, say that the eigenvalues of AC are controllable, the eigenvalues of AUN are uncontrollable. Now, what is the meaning of a eigenvalue being controllable and uncontrollable? We will soon understand that when we look into the state feedback idea. But before I move to the state feedback idea, which I will do in the next lecture, I will have to emphasize this idea of relation between eigenvalues and poles. Again, this was the transform system that we had got, right. Now, if I ask you what is the transfer function of this system, for this system you will say that the transfer function is this, and for this system the transfer function will come out to be this, but since they are related by similarity transform or a transformation of this form, we can show that the transfer function that I get here and the transfer function that I get here will be the same. Okay. So, now if that is the case, why do not we try to find out the transfer function from this formula. So, if I have to find out the transfer function, what is C hat here? C hat is C1, C2, what is Si minus A hat? So, Si minus A hat is Si R minus AC minus A bar 0 Si n minus R A u n minus A u n. This is Si minus A inverse, and then B hat is B1 0 plus D. And what will this come out to be? Look at this, this will be C1, C2. I can actually go ahead and take this inverse in. So, this will be something like this, this will be something like this, and here we will have something. I do not know what it is, but some values will come. Okay. Now, if I do the multiplication here, what am I left with? I am left with C1 Si IR minus AC inverse B1 plus D. So, the transfer function will come out to have an expression like this, okay, and this transfer function and this one has to be the same. What does this tell us about the poles of the system? You remember when we look at the transfer function and look at the denominator of the transfer function, we say that the roots of the denominator are the poles of the system. Now, in this case, what will be the denominator like? So, the denominator, since it is Si R minus AC inverse, it will be some adjugate of Si R minus AC B1 divided by determinant of Si R minus AC plus D. So, you can see that even if I take an LCM, the denominator will come out to be determinant of Si R minus AC, which means that the poles of this system will never have the uncontrollable eigenvalues, right. Okay. So, the poles of this system, the see, this was the system, we had eigenvalues, these were the eigenvalues. Now, the poles of the system will never have the uncontrollable eigenvalues. Now, can I say that the poles of the system have the controllable eigenvalues only because the denominator came out to be determinant of SIR minus AC? Not exactly, because you see, if I go ahead and complete this expression, this will be D determinant of, let me complete this expression. So, this expression will come out to be D determinant of SIR minus AC, but so the top part here might somehow cancel out some factors from the bottom part. So, therefore, not all the eigenvalues of AC may qualify to be a pole of the system. So, there are two things that we can tell about the poles of the system. One is that poles and eigenvalues. One is that the poles of GS will be a subset. Let me write it properly. So, the poles of GS will be a subset of the eigenvalues of A. Not only that, I can make it better. I can also say that the poles of GS will be a subset of the controllable eigenvalues, because the uncontrollable eigenvalues will never be poles of the system. Okay. Now, when will this become equal, we will see soon. Okay. But at least till now I can directly say that if an eigenvalue is uncontrollable, it will never show up as a pole of the system. Okay. So, you see, we have got this new thing now that okay, there is a relation between poles and zeros, poles and eigenvalues. The relation is that first, the poles of the system will be a subset of the eigenvalues of the state matrix, and second, if it is an uncontrollable system, directly you can say that the uncontrollable poles will never be, uncontrollable eigenvalues will never be poles of the system. Now, in the next lecture, we will actually go ahead and understand why are we calling these eigenvalues controllable and uncontrollable. When we started this modern control theory, we define controllability for systems, right? We can go from one state to another. Now I am coming down to a number, a complex number, and telling it this is controllable and that is not controllable, right? So it might confuse you all. I mean, there is nothing to get confused about, okay? Just a nomenclature. As a system, what is controllability? Controllability remains the same. You go from one state to another state in finite time, okay, and you can go from anywhere to anywhere in finite time. That is controllability, okay. That is the definition of controllability. Controllable eigenvalues are the eigenvalues of AC, and uncontrollable eigenvalues are the eigenvalues of AUN. Now, why are they called so? We will get to understand that in the next lecture when we will talk about state feedback for uncontrollable systems. See you in the next lecture. Thank you.